Hello friends, I welcome you in lecture number 12 on higher order ODEs. In previous lecture we have discussed the case of particular integral when right hand side of given differential equation is x raised to m into cos ax or x raised to m into sin ax, and we have seen how to find out particular integral. We had seen that particular integral is 1 over f of d x raised to m into cos ax, and if we have cosine function in the product we have to find a real part of 1 over f of d x raised to m times e raised to I into ax. Similarly, if we have sine function in the product, then instead of real part we have to find out imaginary part of this 1 over f of d x raised to m e raised to I ax. But if power of x is 1, that is if we have x into cos ax or x into sin ax, then we have another shortcut formula for the same particular integral. So today we are going to discuss how to find out particular integral if we have x into cos ax or x into sin ax in the right hand side, but this is applicable only if power of x is 1, and that is very easy and short formula. So first we understand the formula. Suppose right hand side of differential equation is x into gx, where gx is either sine or cosine function, then particular integral is given by 1 over f of d x times gx equal to x outside 1 over f of d is applied to function gx minus derivative of f of d in the numerator, that is f dash d, over square of f of d in the denominator, and this whole quantity is applied to gx. So if we remember this formula, then whenever we have x into sin ax or x into cos ax, it will be easy as compared to method which we have discussed in previous lecture. So today we will explain one example which illustrate the application of this formula, and we can compare that it is very easy as compared to previous formula. So we start with this example. Solve the differential equation y double dash plus 4y equal to x cos x. So first we write in terms of d notation. So y double dash is d square y plus 4y, and we can write by taking y common. So d square plus 4y equal to x cos x. So this is given differential equation in another form. So now first we have to find out the complementary function. For that we solve the corresponding homogeneous ordinary differential equation. So the homogeneous ordinary differential equation corresponding to equation number 1 is written by considering right hand side of 1 equal to 0, that is d square plus 4y equal to 0. Now we solve this equation. For that we require its auxiliary equation. So auxiliary equation is nothing but this quantity equal to 0, and here we have to replace d by lambda. So auxiliary equation is obtained by considering lambda in place of d in this term d square plus 4. So auxiliary equation is lambda square plus 4 equal to 0. That gives us lambda square equal to minus 4, which we can rewrite as 4 into I square, because we know that I square is minus 1. So therefore lambda equal to 2i and minus 2i. So there are two possible values, both are complex. In fact we have pair of complex numbers 0 plus 2i and 0 minus 2i. So therefore the complementary function is c1 times e raised to 0x. 0 is real part here, 2 is imaginary part, e raised to 0x cos 2x plus c2 e raised to 0x sin 2x, and because e raised to 0x is 1, our complementary function is c1 cos 2x plus c2 sin 2x. Now we go for particular integral. So we can see our right hand side is x into cos x, that is power of x is 1. So we can apply that formula. F of d is 1 over d square plus 4. So particular integral is yp equal to 1 over d square plus 4 x into cos x. This is equal to x as it is. F of d is applied to cos x minus, in the numerator we have to write derivative of d square plus 4 with respect to d, which is 2 times d, and here we have to write d square plus 4 whole square, and that we have to apply with cos x. So we are applying this formula. 1 over f of d x gx equal to x times 1 over f of d gx minus f dash d over square of f of d, which is applied to gx. Here f of d is d square plus 4 and gx is cos x. So now we simplify all these things. Now here we have to consider coefficient of x is 1, so we have to replace d square by negative of square of 1, that is minus 1. So we put d square equal to minus 1 here. So we have minus 1 plus 4 cos x, and same thing here. Here also we put d square equal to minus 1. So we have minus 1 plus 4 whole square cos x. So this we obtain by considering d square equal to minus 1. We have put d square equal to minus 1 at 2 places. And now we simplify further. Here we will obtain 3. So we have constant 1 by 3 into x into cos x minus, this is going to be 2d divided by 4 minus 1, 3 square, that is 9 cos x. Now if we consider this d equal to, d is nothing but derivative with respect to x. So derivative of cos x with respect to x is minus sin x, and this we can rewrite as x into cos x over 3 plus 2 by 9 sin x. So this is the particular integral. So this formula is easy as compared to previous formula, and finally we write down the general solution. Therefore the general solution is y equal to yc plus yp. Therefore y equal to, complementary function was c1 cos 2x plus c2 sin 2x plus x cos x divided by 3 plus 2 sin x divided by 9, where c1 and c2 are arbitrary constants. So you can do the same problem in this way also. In earlier lecture we have discussed that this is nothing but real part of 1 over d square plus 4 x into e raised to ix. So you can use that formula also, but if you go in this way and if you compare both the methods, this is going to be very short. Here we have minimum number of steps as compared to this previous method. So you can do the same problem using this formula and compare with this method. You will find that this method is easy, but limitation of this formula is it works only if we have power of x as 1. So we can have one more problem on this. So we consider another problem. Solve the differential equation y double dash minus 2y dash plus y equal to x into sin x. So this also we can write in terms of d. This we can rewrite as d square minus 2d plus 1y equal to x into sin x. Now first we write down the homogeneous differential equation corresponding to this equation. So the corresponding homogeneous ordinary differential equation is d square minus 2d plus 1y equal to 0. So now we solve the auxiliary equation. For this is we replace d by lambda in this f of d. So we have lambda square minus 2 lambda plus 1 equal to 0. So therefore this is nothing but square of lambda minus 1. So we obtain lambda minus 1 equal to 0. It is repeated root lambda equal to 1 comma 1. So we have real and repeated roots or real and equal roots. So therefore complementary function is c1 e raised to x plus c2 x into e raised to x, because we have same function. So we multiply by x, and if we wish we can rewrite this as c1 plus c2x e raised to x. Now for particular integral we apply that ready-made formula. The particular integral is yp equal to our function is d square minus 2d plus 1, and right hand side is x into sin x. So 1 over f of d x into gx. So we use the formula x as it is. 1 over d square minus 2d plus 1 is applied to sin function minus derivative of d square minus 2d plus 1 with respect to d is 2d. Derivative of d square is 2d minus derivative of 2d is 2, and derivative of 1 is 0. And here we write d square minus 2d plus 1 whole square, and that is applied to sin x. Now because we have sin x and here coefficient of x is 1, so we put d square equal to minus 1 square, that is minus 1. So here we put minus 1 minus 2d plus 1 sin x. Here we can take 2 common, so we have d minus 1 in the numerator, and here also we replace d square by minus 1, that is minus 1 minus 2d plus 1 whole square sin x. So here we have replaced d square by minus 1. Now we simplify this, so you can see 1 minus 1 is 0, and we have minus x by 2. This is going to be minus 2d, that is multiplied with 1 over minus 2d into x. So we write minus x by 2, and 1 over d will be applied to sin x. Minus 2 times d minus 1. Here we will have 1 minus 1 0, and square of minus 2d, which is applied to sin function. Now as we know, because d means d by dx, 1 over d is integral of sin x with respect to x. So integral of sin x is minus cos x. Here minus 2 times d minus 1, and this becomes 4 times d square sin x. And this we can rewrite as negative negative positive x into cos x over 2. Here minus 2 by 4, that is going to be minus 1 by 2 d minus 1 as it is, and again we put d square equal to minus 1. So here we have minus 1, and we are using that coefficient of x in sin x is is 1. So we have minus 1 square, that is minus 1. So we replace this d square by minus 1. Now again we simplify. This is as it is, x into cos x over 2. Here negative negative positive, 1 by 2, and d minus 1 will be applied to sin x. Now d means derivative, x into cos x over 2 plus 1 by 2, d of sin x means derivative of sin x, which is cos x, and minus 1 into sin x. So this is the particular integral. If we wish, we can take 1/2 common. So we have x into cos x plus cos x minus sin x. So in this way we can obtain particular integral using this short formula. So in the next step we have to write general solution. So therefore the general solution is y equal to complementary function plus particular integral, and therefore y equal to complementary function was c1 plus c2x e raised to x, and here we have plus 1/2. Now we are writing this x into cos x plus cos x minus sin x, where c1 and c2 are arbitrary constants. So in this way we can use that formula to find out particular integral when Rx is in this form, x into gx, where gx is either sin ax or cos ax. So this is another interesting shortcut formula, 1 over f of d x into gx equal to x as it is 1 over f of d gx minus, here we have to write square of f of d, here derivative of f of d with respect to d applied to gx. So this becomes very easy. We can in very short time we can find out the particular integral, but limitation is here power of x must be 1. But if power of x is more than 1, we have to use the formula which we have discussed in previous case, that is this formula. We have to find out real and imaginary parts. So this is all about this lecture. I hope you like it. Thank you.